Hello, in this video we're going to go over this problem. Find all positive integers n for which phi of n divides n. Just to remind you, phi of n is the number of positive integers less than or equal to n that are relatively prime to n. Okay, and this one is called Euler's Totient function. So for example, if you have a prime p, Euler's Totient function is p minus 1 because all of the numbers from 1 through p minus 1 are relatively prime to p. If you have a prime p squared, then you have p squared numbers. All the multiples of p, including p, 2p, all the way to p times p, these are all not relatively prime, so we'll have to subtract them. And if you have phi of p to the power of k, then that would be p to the power of k, all the numbers from 1 through p to the power of k, minus all the multiples of p, so minus p to the power of k minus 1. And it can also be shown that phi of mn is equal to phi of m times phi of n if m and n are relatively prime. So, and this is a well-known fact in number theory. So in general, if you want to find phi of, let's say, 2 to the power of 5 times 3 to the power of 7, I'll give you an example and then I'll tell you how to solve the problem. You can rewrite that as phi of 2 to the power of 5 times phi of 3 to the power of 7. Now we know how to evaluate each one of them. This one is 2 to the power of 5 minus 2 to the power of 4 based on the discussion that we just had. And the next one is 3 to the power of 7 minus 3 to the power of 6. So in general, if you have the prime factorization of a number, p1 to the power of alpha 1 all the way to pk to the power of alpha k, this is going to be phi of p1 to the power of alpha 1, which is p1 to the power of alpha 1 minus p1 to the power of alpha 1 minus 1, all the way to pk to the power of alpha k minus pk to the power of alpha k minus 1. Now, if you call this number n, then phi of n becomes, so the rest of them become, if you factor p1 to the power of alpha 1 from the first one and pk to the power of alpha k from the last one, we get 1 minus 1 over p1 all the way to 1 minus 1 over pk. And this is also n. So what they're asking us is, when is it that this number divides n? So phi of n divides n. So what does that mean? It means if I take the ratio of n over phi of n, that would have to be an integer. So if I do that, I would get n over phi of n, which is n times 1 minus 1 over p1 all the way to 1 minus 1 over pk. So this would have to be an integer. So if I cancel n and take the common denominator, I will get p1, p2 all the way to pk divided by p1 minus 1 all the way to pk minus 1. And let's assume that p1 through pk are in increasing order. So let's say p1 is less than p2 less than pk. So what I need is p1 minus 1 all the way to pk minus 1 to divide the product of p1 through pk. Now, one thing, it becomes pretty clear here. If you look at p1 minus 1, p1 minus 1 is less than every prime on the right. So that means p1 minus 1 cannot divide any of the primes unless it is 1, because the only number that is less than a prime dividing it would be 1. So this means p1 minus 1 must be 1, since p1 minus 1 is less than p1, less than p2, less than pk. So the only number that divides the product of p1 through pk is in fact 1. And that is less than p1. So that means the first number must be 2. So one of the possibilities would be when you have n equals 2 to the power of m. So if n is 2 to the power of n, then phi of n would be 2 to the power of m minus 2 to the power of m minus 1, which is 2 to the power of m minus 1. And that, of course, divides 2 to the power of m. Now, it's also possible that n doesn't have any prime factor, so n equals 1. That gives us phi of 1 equals 1, and that, of course, also divides 1. So we found two different sets of solutions, 1 and 2 to the power of m, and in fact 2 to the power of m, if m is 0, it would be also 1. Okay, so we found some solutions. Now, are these all solutions? We know that the first prime would have to be 2. So let's rewrite that. So we get 2 minus 1 times p2 minus 1 all the way to pk minus 1 would have to divide 2 p2 all the way to pk. Okay, so all of these primes here are in fact odd because we know that p2 is more than 1. So all of them are odd, so it means this side is divisible by 2 to the power of k minus 1. There are k minus 1 primes on the left besides 2, so that would have to be divisible by 2 to the power of k minus 1. But this is only divisible by 2. What does that mean? It means not divisible by 4, because all of the pi's are odd. So since that's not divisible by 4, that tells us that k must be 2. So you cannot have more than one prime other than 2. So that tells us we have 2 minus 1, which is just 1, p2 minus 1, that divides 2 times p2. Now, of course, p2 minus 1 does not divide p2. In fact, they are relatively prime. GCD of p2 minus 1 and p2 is 1. So because of that, p2 minus 1 must divide 2, which means p2 must be 3. Okay, so in that case, I get n equals 2 to the power of m, 3 to the power of l. Let's evaluate phi of that and see what we get. So phi of n equals phi of 2 to the power of m times phi of 3 to the power of l. This would be 2 to the power of m minus 2 to the power of m minus 1 times 3 to the power of l minus 3 to the power of l minus 1. This is equal to 2 to the power of m minus 1, factor 3 to the power of l minus 1, and you will get 3 minus 1. So this would be 2 to the power of m, 3 to the power of l minus 1. And that, of course, divides n. To summarize what we got that phi of n divides n if and only if either n is equal to 2 to the power of m for some non-negative integer m, or n is equal to 2 to the power of m times 3 to the power of l for some m that is positive and l that is non-negative. So, and this brings me to the end of this video. So I will see you in the next video.